6.2, some difference in double angle identity. So let's do a quick startup before we get going here. This will be good practice because we will encounter this all the time when we're doing problems involving trig identity. So I'm going to put a box around that says that's number 1, number 2, and then number 3. I'm going to look at 3 separate cases here where I'm going to have non-permissible values or restrictions. I'm going to leave this one alone because I don't have any case where a cosine of x could be undefined, right? So I'm going to leave that alone. Number 1, that's number 1 is this is in the denominator. So secant of x minus 1 equals 0. That whole thing, how do I get it to be equal to 0? So secant of x equals 1. That's 1 over cosine of x equal 1. Well, how do I get this equal to 1? What does cosine of x have to be equal to 1? So I'm going to isolate that. Cosine of x equal 1. X equals the inverse cosine of 1. So where is cosine of x equal to 1? That is at every 2 pi n, where n is an element of integers. So if n equals 0, x equals 0. So cosine of 0, does that equal 1? Of course it does. What if n equals 1? That's 1 full revolution counterclockwise. So x equals 2 pi for an n value of 1. What's cosine of 2 pi? Well, we're still at, that's 2 pi radians, counterclockwise, one rotation. That is cosine of 2 pi equals 1. That works. What if n is negative 1? So that's x equals negative 2 pi. Cosine of negative 2 pi, that's just one revolution or one rotation in the clockwise direction. And we're back to that positive x-axis spot. So the cosine of negative 2 pi is still 1. So this is our solution. So we can say that for this part, the non-permissible value is x does not equal 2 pi n. N is an element of integers. Okay, so I'm going to put a box, or let's put a bubble around that. That's number 1. Number 2, I have cosine of x minus 1. Well, I don't want that to be equal to 0, so I'm going to set it equal to 0 to see what is this x value that will give me 0. Okay, so I do cosine of x. I'm going to add 1 to both sides. And now I'm left with this case where I'm solving for x, the inverse cosine of 1. Well, that's this same case up here. Okay, so we've already done that work. So x equals 2 pi n. N is an element of integers. So if I state it like this, the non-permissible value in this case is x does not equal 2 pi n. N is an element of integers. Okay, let's bubble that. Number 3. This last part, I have secant of x. It's in the numerator, so secant of x plus 1 equals 0. That's okay. That's permissible. I'm just going to focus in on secant of x. So if I'm being super accurate here, my box should just include secant of x, right? So secant of x, where is this expression? Where is this undefined? Well, let's take a look at this. Secant of x, that equals 1 over cosine of x. Okay. What value of x makes 1 over cosine of x undefined? Okay, so I need cosine of x to be equal to 0 to make this expression undefined. So let's do that work. X equals inverse cosine of 0. Well, what is that value? Well, we know that pi over 2 cosine of pi over 2 is 0. Okay, and then we go another 180 degrees or another pi radians. Its cosine is still going to be 0. So it's pi over 2, general solution is x equals pi over 2 plus pi n, where n is an element of all integers. So when I state my non-permissible value for this, NPV, that is x does not equal pi over 2 plus pi n, where n is an element of integers. So let me put a bubble around that. So I have this set, which is the same as this set, and I have this set. So which of the choices matches? So right here, B. Okay, so good little startup there. Just a reminder of, hey, we always have to be checking for our non-permissible values. Let's get into sum and difference identities. For the sum and difference of any two angles, alpha and beta, so I'm right here, we have a sum and difference identities. The sum and difference identities can be used to simplify expressions and to determine the exact values of some trig ratios. These are on the formula sheet. For this lesson, I'm not going to get into how I derive these. I'll do a separate video, and I'll embed it into this lesson, and also it's a separate video as well that shows the proof of how do I get all these identities. Okay, so I'll do a separate video. I have the sum identities, sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. Cosine of alpha plus beta equals cosine of alpha cosine of beta minus sine of alpha sine of beta. I have the tangent sum identity. Tangent of alpha plus beta equals tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha tangent of beta. Difference identities. Sine of alpha minus beta equals sine of alpha cosine of beta minus cosine of alpha sine of beta. Cosine difference identity. Cosine of alpha minus beta equals cosine of alpha cosine of beta plus sine of alpha sine of beta. Tangent of alpha minus beta equals tangent of alpha minus tangent of beta divided by 1 plus tangent of alpha tangent of beta. Okay, these are on your formula sheet. Should I memorize these? Sure, right? But I'll show you the derivations in a separate video. It will make more sense where they come from, but ultimately it takes practice to get used to what these look like, but you'll always have it handy on your formula sheet. Go to the end of the lesson for the proof of the sum and difference identities for sine, cosine, and tangent. Example 1, algebraically determine the exact value. So exact values means no decimals, okay? So when I have something like cosine of 165, well, normally, like I'm thinking, like, do I need a calculator? Or like it's not one of these angles where I know the exact value, right? So how do I do this? So I need to think about two angles that either add or subtract to 165, and I use my sum or difference identity to evaluate. So here's the trick here. So you kind of just have to play around with this or think about it. 165, how can I represent it as the sum of two of these primary angles, right? Or these important unit circle angles? Well, I think about, well, let's see, 45 degrees plus 120. Well, that works. Okay, if I tried 30, I know the exact value of the trig functions for 45 and 120. I know the exact value for 30. Well, if I do 30, that's 30 plus 135. Okay, that works as well. So you have more than one choice, right? I'm going to stick with 45 and 120. You can try it both ways, but let's stick with this fact. 165 equals 45 degrees plus 120 degrees. So I rewrite it like this. Cosine of 165, that is cosine of 45 degrees plus, that's cosine of 45 degrees plus 120 degrees. Well, right underneath it, I'm going to write my cosine sum identity. Cosine of alpha plus beta. Well, from our formula sheet, that's cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. So in this case, when I am substituting in alpha equals 45 degrees, beta equals 120 degrees. So let's do cosine of 165 equals, actually let me write it this way. It's cosine of 45 degrees plus 120 degrees. That equals cosine of 45 degrees, cosine of 120 degrees, minus sine of 45 degrees times sine of 120 degrees. We know the exact values of all these cosine and sine values. Okay, all these cosine and sine ratios. Cosine of 45, that's square root of 2 over 2. Cosine of 120, that is in the second quadrant. Okay, right here. And that's going to be my x value, so that's negative 1/2. Minus sine of 45, well, that's square root of 2 over 2. And sine of 120, that's in quadrant 2, that's going to be my y value. Okay, so that is square root of 3 over 2. And then let's evaluate. The rest is evaluate. And again, notice I have all exact values. Okay, so that's negative square root of 2 over 4 minus square root of 6 over 4. And then when I combine that, I get negative square root of 2 minus square root of 6 divided by 4. So there's my final answer, exact value. Okay, be careful when it asks for exact values. All right, letter B, sine of pi divided by 12. So how can I represent pi divided by 12 as the sum or difference of two angles that I know the exact values for? Well, pi over 12, if I'm thinking like 12, what about 4 pi over 12 and 3 pi over 12? That equals pi over 12. Well, 4 pi over 12 is just pi over 3 in disguise, and 3 pi over 12 is pi over 4 in disguise. So do I know the exact values of pi over 3 and pi over 4? Of course I do. All right, so I will write it as sine of pi over 12 equals sine of pi over 3. Come on. Sine of pi over 3 minus pi over 4. And that equals sine of alpha minus beta. And I know that equals my identity, my difference identity, cosine of alpha, cosine of beta, minus cosine of alpha, sine of beta. Okay, so I will do my substitution. That's sine of pi over 3 minus pi over 4 equals sine of alpha, which is pi over 3. So alpha equals pi over 3, beta equals pi over 4. Sine of pi over 3 cosine of pi over 4 minus cosine of pi over 3 sine of beta, which is pi over 4. Sine of pi over 3, that is exact value, square root of 3 over 2. Cosine of pi over 4, square root of 2 over 2. Minus cosine of pi over 3, that is 1/2, folks. Yep. And sine of pi over 4, that's square root of 2 over 2. And let's simplify that. Square root of 6 over 4 square root of 6 over 4 minus square root of 2 over 4, and that equals square root of 6 minus square root of 2 over 4. And again, these are exact values. Tangent of 285. So similar trick here. 285 degrees equals, well, if you play around with a little bit, I get 225 degrees plus 60 degrees. Okay, so tangent of 225 plus 60 degrees, and right underneath it, tangent of alpha plus beta. Our sum identity for tangent is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha, tangent of beta. Okay, where alpha equals 225 degrees and beta equals 60 degrees. So tangent of 225 degrees plus 60 degrees equals tangent of 225 degrees plus tangent of 60 degrees divided by 1 minus tangent of 225 degrees times tangent of beta, which is 60 degrees. Okay, let's insert our exact values. Tangent of 225 is 1 plus tangent of 60, that is square root of 3 over 2 divided by 1/2, that is plus square root of 3, divided by 1 minus, what's tangent of 225? That is in quadrant 3. It is positive, so that's 1, times, what's the tangent of 60? Well, it's square root of 3. And let's simplify. 1 plus square root of 3 over 1 minus square root of 3. Okay, as habit and good practice, exact values, but we need to rationalize our denominators. So I'm going to multiply by the conjugate, 1 plus square root of 3. So this is a version of 1 that I'm multiplying by, so I'm not changing the value. That's 1 plus square root of 3 times 1 plus square root of 3 divided by 1 times 1 is 1. I have no middle term, and then minus square root of 3 times square root of 3 is 3. And that equals, let's FOIL this, 1 times 1 is 1, plus square root of 3 plus square root of 3 plus square root of 3 times square root of 3 is square root of 9, and that is 3 divided by negative 2. That is 4 plus 2 square root of 3 divided by negative 2. Okay, I'm going to factor out a 2, so that's 2 plus square root of 3, and that's negative 2. 2 divided by negative 2 is negative 1, so I have negative 1 times 2 plus square root of 3, or negative 2 minus square root of 3. Next page. Simplify each expression as a single trig ratio. So some of these, it's going to give you the expanded form, and then I have to think about what sum or difference identity does this look like. So for this one, this pattern I see, well, when I see that, well, I see 8x, 2x repeated, then I see cosine, cosine, sine, sine. I look through my formula sheet and I say, well, that looks like the difference identity for cosine. So I'm going to think of it this way. Alpha equals 8x. Alpha equals 8x. And beta equals 2x. Okay, so I'm thinking alpha, beta, because I see that pattern in the cosine difference identity. So cosine of alpha minus beta equals, well, cosine of alpha cosine of beta plus sine of alpha, sine of beta. So when I plug this in, cosine of alpha is 8x, beta is 2x, equals, let's plug this in, cosine of 8x, cosine of 2x, plus sine of 8x, sine of 2x. Well, this whole part looks exactly like this. So we know we did this correctly. So right here. So we want a single trig ratio, single expression. So this part here, that's cosine of 8x minus 2x is cosine of 6x. And that's our single trig ratio. Okay, letter B, sine of pi over 2 minus x. So again, alpha equals pi over 2, beta equals x. This is the sine difference identity, so I'll write it as sine of alpha minus beta equals sine of alpha cosine of beta minus cosine of alpha sine of beta. When I line this up, I have sine of pi over 2 minus x. Let me plug in my alphas and betas. So sine of pi over 2 cosine of x minus cosine of pi over 2 sine of x equals sine of pi over 2 is 1 times cosine of x. Cosine of pi over 2 is 0 times sine of x. This is 0, and then I'm left with a single trig ratio, cosine of x. Letter C, cosine of pi over 4 minus x times secant of pi over 4 minus sine of pi over 4 minus x times cosecant of pi over 4. Let's see, what do we have here? First off is, let me take care of these two right here, because I see a cosine difference identity, I see a sine difference identity. Let me evaluate these first, and then plug those in, okay? So the secant of pi over 4, I think of that as 1 over the cosine of pi over 4. Well, that equals 1 over square root of 2 over 2, and that equals 2 over square root of 2. How about the cosecant of pi over 4? Well, that equals 1 over the sine of pi over 4. Well, that equals 1 over square root of 2 over 2, and that equals 2 over square root of 2. Okay, so I'm going to plug those in. Cosine of pi over 4 minus x times, oh, let me do this so it's not confusing. So I'm going to put this out in front. So that's 2 over square root of 2 cosine of pi over 4 minus x minus, let's put this out in front, 2 over square root of 2 sine of pi over 4 minus x. This one, cosine difference identity, so that's 2 over square root of 2 times cosine of pi over 4 cosine of x plus sine of pi over 4 sine of x minus 2 over square root of 2 times, this is the sine difference identity, so that is sine of pi over 4 cosine of x minus cosine of pi over 4 sine of x. Let's evaluate all the stuff inside the brackets. Cosine of pi over 4 is square root of 2 over 2, and cosine of x is just cosine of x, plus sine of pi over 4 square root of 2 over 2 times sine of x minus 2 over square root of 2 sine of pi over 4 square root of 2 over 2 cosine of x minus cosine of pi over 4 is square root of 2 over 2 sine of x. Let's distribute this across. So 2 times square root of 2 times 2 over square root of 2 times square root of 2 over 2 is 1. So that first term is cosine of x, and the second term is sine of x, minus, same deal here, 2 divided by square root of 2 times square root of 2 over 2 is 1. So I have minus cosine of x minus sine of x. Let's evaluate through the brackets. That's cosine of x plus sine of x minus cosine of x plus sine of x. Cosine of x minus cosine of x is 0. Sine of x plus sine of x, that equals 2 sine of x. Okay, this last one, let us turn it into a single trig identity. This looks familiar, right? This looks like one of either the sum or the difference tangent identity. So the sum or difference identity for tangent. Well, I see this minus sign here. I'm thinking the difference identity, right? So I'm checking it against my formula sheet where alpha equals pi over 2 and beta equals pi over 3. So if I'm thinking tangent of alpha minus beta equals tangent of alpha minus tangent of beta divided by 1 plus tangent of alpha tangent of beta. Okay, that's tangent of alpha minus beta, so pi over 2 minus pi over 3. And is that the case? Let me write this out in full. Tangent of pi over 2 minus tangent of beta, which is pi over 3, divided by 1 plus tangent of alpha, which is pi over 2, times tangent of beta, which is pi over 3. Okay, so this checks. This looks exactly like this, right? So I'm going to focus on this. Let's shrink that into a single trig function. So pi over 2, I need common denominator. So I'm going to go 3 pi over 6 minus 2 pi over 6. And that is tangent of pi over 6. There's my single trig ratio. Okay, example 3. Given angle M in standard position with its terminal arm in quadrant 3 and cosine of M equals negative 5 over 13, and angle N in standard position with its terminal arm in quadrant 1 and sine of N equals 3/5, algebraically determine the exact value of cosine of M minus N. Wow, okay. So I know cosine of M minus N. Let's write out the difference identity for cosine of M. Cosine of n. Let me put some brackets around this because I got lots of letters going on. Cosine of m, cosine of n, plus sine of m, sine of n. Okay, and then I said cosine of m equals negative 5/13, and sine of n equals 3/5. Okay, so the goal here is I'm trying to algebraically determine these. I have sine of n, I have cosine of m, but I need cosine of n and sine of m. So what do I need to do here? I need to set up some triangles here in the correct quadrants. So if I set this up for, let's first start with the cosine. Cosine of m equals -5/13. So if I have my angle in standard position like this, this is my angle m, and so the cosine is adjacent over hypotenuse, -5/13. This one right here. Okay, and then you can do Pythagorean theorem, or I just know this is a Pythagorean triplet. This sine of m value has to be -12. Okay, so that's a Pythagorean triplet. 5 squared, -5 squared plus -12 squared equals 13 squared. Okay, so that is -12. So my sine of m from this triangle that I have here, sine of m equals opposite, -12 divided by 13. So -12/13. Okay, let's do the cosine. Let's do angle n. So we know that's in the first quadrant. There's angle n. And sine of n equals opposite, 3 over hypotenuse, 5. Well, I know the other leg of the triangle is 4 because it's a Pythagorean triplet. Or I think about 3 squared plus 4 squared equals 5 squared. Okay, so I can find the cosine of n is adjacent, 4 over hypotenuse, 5. Oh, hang on. I think sine, yeah, okay. Now I'm just checking my answers here. Sine of n is 3/5, got it. Okay, and then cosine of n is adjacent, which is 4/5. Okay, so I got that. Now I'm going to take this equation here and let's plug in all our values. So cosine of m minus n equals cosine of m times cosine of n plus sine of m times sine of n. Let's plug all these in. Cosine of m is -5/13. Cosine of n is 4/5. Plus sine of m is -12/13. And sine of n is 3/5. Okay, so that is, let's just do a little bit of this arithmetic here. That's -20/13 times 5 is 65. Plus -36 over 65. Okay, and then that's -20 plus -36 over 65, and that equals -56/65. Howdy folks, deriving the sum and difference identities for trigonometry. So I have this wonderful rectangle ABCD with a triangle AEF inscribed in it. I'm going to make a couple of labelings here. So I'm going to call this angle alpha. I'm going to call this angle bravo. I'm also going to call the hypotenuse of triangle AEF, so side AF, I'm going to say that is 1 unit. Okay? All right, so using a series of just basic right triangle trigonometry and some properties of angles, I'm going to derive sum and difference identities. So let's get started here. So for triangle AEF, so I'm going to look at triangle AEF. I'm going to take the sine of beta, and I'm looking at this opposite side. So sine of beta equals opposite over hypotenuse, which is just 1. And that means that the opposite side is equal to sine of beta. So making that hypotenuse 1 greatly simplifies our derivation. So I will call this sine of beta. Okay, let's do the same thing with the cosine of beta. Well, that's the adjacent side here. Cosine of beta is adjacent divided by the hypotenuse, which is 1. And so the adjacent side equals cosine of beta. So let's label that. So the adjacent side here is cosine of beta. Let's look at triangle ABE this time. And let's do the same thing except with angle alpha. So I'll do the sine of alpha, and that equals, so the sine value, I'm looking for the opposite side. So the sine of alpha equals opposite. In triangle ABE, the hypotenuse is cosine of beta. So my opposite side equals sine of alpha cosine of beta. Okay, so let me update that. Sine of alpha cosine of beta. Sine of alpha times cosine of beta. There we go. I'm going to also take the cosine of alpha, and I'm looking for this adjacent side. That is adjacent divided by, well, it's hypotenuse, cosine of beta. So that leads me to adjacent side equals cosine of alpha cosine of beta. Okay, so let me fill that in. Cosine of alpha cosine of beta. Okay, good so far? Okay, next one, let me look at this angle here. So I'm going to highlight it. If I highlight this angle, folks, and this angle, well, I know side A, B. Okay, so I'm looking at those two angles. Okay, let me just take that back. I know that AB is parallel to DC. Okay, therefore, what does that tell me about angles? Therefore, it tells me that angle, so if I have a transversal that cuts across two parallel lines, they will form alternate interior angles that are equal. So AB is parallel to DC, okay, with transversal AF. That tells me angle BAF equals angle AFD. So the measure of angle BAF equals the measure of angle AFD. Why is that important? Because then now I can say this angle is alpha plus beta. How do I know that? Well, let me just highlight this. Here's alpha plus beta. Here's alpha plus beta. Okay? All right, why is that important? Well, I'm going to continue with this new angle of alpha plus beta. Now I'm in triangle Folks, now I'm in triangle AFD. AFD. I'm going to do the whole same process again. Let me do the sine and cosine ratios of this triangle. So sine of alpha plus bravo equals, well, I want this opposite side. So that's opposite divided by, what's the hypotenuse? It's 1. So this tells me that the opposite side equals sine of alpha plus bravo. Sine of alpha, sine of alpha plus bravo. Okay? Oh, come on, neatness. Sine of alpha plus bravo. There we go. Okay? Now let's do the adjacent side. I have cosine of alpha plus bravo. That equals the adjacent side divided by the hypotenuse. So the adjacent side divided by the hypotenuse, that's still 1. And that gives me the adjacent side equals cosine of alpha plus bravo. Okay, so let me fill that in here. This is cosine of alpha plus bravo. Okay, last triangle we need to do here okay, is triangle CEF. Okay, before we do triangle CEF, I need to understand the angles that I'm dealing with here. Okay, so here's the way I look at it. I don't know what this angle is or this angle is, right? All I really need is one angle. And let's find this angle. Well, I think it's alpha, but how do we know it's alpha? Let's reason this out. So I'm going to call this angle K. So in this triangle, I have alpha plus K plus 90. That equals 180 degrees, correct? We know that. We know that also 3 angles along a straight line. So in this case, this straight line right here, K, 90, and question mark. Okay, so on that straight line, so on that straight line, I have, where should I put it? Right here. Angle K, K plus 90 degrees. So K plus 90 degrees plus question mark, that also has to equal 180. Well, I just said this part is equal to 180. So alpha, so I'm going to put it this way. I said alpha, I said alpha plus K plus 90 degrees equals 180 degrees. This one, let me rewrite it in order matching, right? So K plus 90 plus alpha equals 180 degrees. This question mark, because both equal 180 degrees, that has to be alpha. So that's why this angle is alpha. Okay? All right. Now that we got that established, let's go back and let's calculate the sine and the cosine ratio for each of these values. Okay, so first, triangle CEF, sine of alpha equals, well, I'm looking for this opposite side. So let me just move all of this. Okay, I'm going to just erase this, folks, right here. I got to make some room. Okay, I'm looking for this opposite side here. Sine of alpha equals opposite over, well, the hypotenuse in triangle CEF is sine of beta. So that gives me opposite side equals sine of alpha, sine of beta. Sine of alpha, sine of beta. Okay, let's do the adjacent side here. I'm doing the cosine of alpha, and that equals adjacent divided by, well, the hypotenuse is sine of beta. So my adjacent side is equal to cosine of alpha, sine of beta. Let's fill that in. Cosine of alpha, sine of beta. Okay? All right. What will I do with all this? Okay? What will I do with all this? Let's take a look at let's compare the sides of the rectangles to each other. I have a rectangle. Okay, one thing I will pencil in here is that's a 90-degree angle. So we know that opposite sides of a rectangle, they're not only parallel, but they're also equal in length. So if I look at the vertical sides first, here and here, okay, so if I do AD is equal to BC. So let's first state that AD, the length of AD equals the length of BC. We know that from a rectangle. Let's substitute in for AD. When I do that, AD is sine of alpha plus bravo. And BC, look on the left side, here and here, that is equal to sine of alpha cosine of beta plus cosine of alpha sine of beta. Okay, if you look at your trig identities, your sum identities, this is it right here. Okay, fabulous. Let's do the other side of the triangle. Here, I know that side AB is equal to side DC, and I know this because these are the opposing parallel sides of a rectangle are equal. So side AB, that is cosine of alpha cosine of beta, equals, well, what's side DC? That is cosine of alpha plus beta plus sine of alpha sine of beta. All right, let me make this look like our cosine sum identity. So let me cosine of alpha cosine of beta equals, oops, I'm going to subtract this from both sides. So what do I get? Minus sine of alpha sine of beta equals cosine of alpha plus beta. let me just write it left to right with the cosine of alpha plus beta on the left side. That equals cosine of alpha, cosine of beta, minus sine of alpha, minus sine of alpha, sine of beta. Okay? This one, and this one. This is our sum identity for sine. This one is our sum identity for cosine. Okay? Well, how do I get the difference identities? For the difference identities, folks, just a subtle manipulation, but we'll show you how this works. So if I start with the sine sum identity, sine of alpha plus alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. Let me turn this into a difference identity by doing this. I'm going to go sine of alpha plus negative beta, and let's make that substitution. So sine of alpha cosine of negative beta plus cosine of alpha sine of negative beta. Okay? The left side is sine of alpha minus beta. There's the format for our difference identity, but what happens on the right side? So off to the side here, right? When I have the sine of negative theta, this is a handy identity to know. This is equal to negative sine of theta. When I have the cosine of negative theta, that is the same as just cosine of theta. Well, I'm going to do a brief segue here. I want you to understand through some graphs. I'm going to draw this out. I want you to understand why this is true. So if I say theta for this one, theta equals pi over 4, what's the sine of pi over 4? That's square root of 2 over 2. Okay? If I do theta this way, where theta equals negative pi over 4, so I'm going clockwise, and we know that's a negative angle, what's the sine of negative pi over 4? Well, it's in quadrant 4. The sine ratio represents the y value. We know that's negative square root of 2 over 2. Okay, so if I line this up, if I say the sine of negative pi over 4 equals, well, I have to adjust the positive version of the angle, sine of pi over 4, by negative 1 so that it's true. Let's take a look. Sine of negative pi over 4 we said is negative square root of 2 over 2 equals negative 1 times what's sine of pi over 4? Square root of 2 over 2. So negative square root of 2 over 2 equals negative square root of 2 over 2. Therefore, we can conclude that sine of negative theta equals negative sine of positive theta. Okay, so that's a very important identity right there. That's the first one. Folks, the cosine version. Draw another graph. Call this theta. Theta equals pi over 4. Let's use the same one. What's the cosine of pi over 4? That equals square root of 2 over 2. Let's do theta the other way, where theta equals negative pi over 4. What's the cosine of negative pi over 4, folks? That's cosine of negative pi over 4. I'm still going to the right, my x value, that's still square root of 2 over 2. So what does that tell me? Cosine of negative pi over 4 equals cosine of pi over 4. Well, we know that because square root of 2 over 2 equals square root of 2 over 2. So therefore, in general terms, cosine of negative theta equals cosine of theta. Okay? And that's our second one. Okay, so let's use this to our advantage when I look at sine of negative beta and cosine of negative beta. That equals sine of alpha. What's the cosine of negative beta? Right here. It's just cosine of positive beta plus cosine of alpha. What's sine of negative beta? That's times negative sine of positive beta. Let's finish this up, clean it up. Sine of alpha minus beta equals sine of alpha cosine of beta. This negative sine of beta, I'll bring the negative sign out here. Cosine of alpha, sine of beta. This is our sine difference identity. So this is our difference identity. Okay. Let's do the cosine identity for difference. So I'm going to start with cosine of alpha plus beta equals cosine of alpha cosine of beta minus sine of alpha sine of beta. Okay? Similar to what we just did, I'm going to go cosine of alpha plus negative beta equals, and let's make the substitution. Cosine of alpha, cosine of negative beta, minus sine of alpha, sine of negative beta. So we have these two identities here. I'm going to plug those in. So cosine of alpha minus beta, there's our difference identity. Cosine of alpha, cosine of negative beta is just cosine of beta, minus sine of alpha, and I know sine of negative beta is negative sine of positive beta. Okay, let's clean this up. Negative and negative is positive, and I end with sine of alpha, sine of beta. This is our cosine difference identity.